For decades, the standard cosmological model, lambda CDM, has mapped the dawn of the universe. By combining cold dark matter with a cosmological constant, it explains the distribution of the earliest light and the large-scale structure we see today. This is a graph of the universe's expansion rate, the Hubble constant. Based on observations of the cosmic microwave background from the Planck satellite, the standard model predicts the universe should be expanding today at 67.4 kilometers per second per megaparsec. When astronomers measure that expansion rate directly in the local universe, they find a different result. Using the local distance ladder, the SHOES team measures the current expansion rate at 73.17. The gap between these two numbers represents a 5.8 sigma discrepancy. Statistically, there is less than a 1 in a million chance that a difference this large is a simple fluke. This leaves two possibilities. Either the complex observational mechanics used to measure the late universe are affected by unseen systemic errors, or there is an undiscovered physical mechanism operating at low redshifts. By auditing the late universe probes step by step, we can test the error hypothesis. If the observational tools hold up, the gap is real, and the lambda CDM model is reaching its limit. Measuring cosmic expansion requires building a local distance ladder by cross-calibrating objects in 3 steps. We begin at the base, the anchors. Astronomers rely on Gaia satellite parallaxes, detached eclipsing binaries, and water masers in galaxies like NGC 4258. These methods are rooted in triangulation and orbital mechanics. By using local geometry, astronomers can calculate distances without relying on an assumed cosmological model. To ensure calibration holds, measurements are cross-referenced across nearby galaxies. Astronomers calculate exact distances to the dense stellar populations inside the Large Magellanic Cloud. They then verify those results in separate environments, checking the geometry against detached eclipsing binaries found within the neighboring Small Magellanic Cloud. By grounding the first rung in direct geometric measurement, astronomers minimize the risk of calibration bias before the latter even reaches the first star. Once the geometric distances are locked in, they are used to calibrate the ladder's second rung, standard candles. For decades, the preferred standard candle has been the Cepheid variable star. Cepheids pulsate. Timing a Cepheid's pulse reveals its intrinsic absolute magnitude. Comparing this known brightness to how dim it appears from Earth gives its distance. But measuring Cepheids in distant galaxies introduces a vulnerability known as crowding. Deeper in space, a single Cepheid's light can blur with surrounding stars, potentially skewing the results. To test if crowding was inflating the Hubble constant, astronomers audited these exact Cepheids using the superior optical resolution of the James Webb Space Telescope. The new data cleared away the background interference. The dispersion in the period luminosity relation tightened significantly, dropping from 0.45 magnitudes down to 0.17. These sharper measurements rule out unrecognized crowding as the primary cause of the Hubble tension, with a confidence level of 8.2 sigma. Even secondary concerns, like differences in star composition and interstellar dust, are accounted for. By applying Rednin-free Wesenheit magnitudes, astronomers can isolate the true luminosity regardless of the dust in the way. With the crowding hypothesis largely resolved, the source of the tension becomes increasingly difficult to attribute to the local calibration of Cepheids. The Cepheid distances are used to calibrate the final rung of the ladder, Type 1a supernovae. To do this, astronomers apply the TRIP formula. This equation standardizes the light curves of these supernovae explosions, accounting for their color and host galaxy properties to turn them into reliable cosmic yardsticks. These standardized events act as beacons that can be identified and measured deep into the cosmic background. To properly calculate the Hubble constant, these supernovae must be observed far beyond local space, specifically deep into the Hubble flow at redshifts approaching 0.15. At these extreme distances, the universe's expansion overpowers the gravitational pull of local galaxy clusters. It filters out the noise of local peculiar velocities. From pure geometry to standardized deep space supernovae, the cumulative mechanics of the latter hold firm. The local measurement of 73.17 is the result of multiple cross-verified steps. We can stress test this conclusion by bypassing the Cepheids entirely and swapping in a different type of standard candle, using the tip of the red giant branch. Before a red giant undergoes a thermonuclear helium flash, it reaches a highly uniform peak luminosity. This Hertzsprung-Russell diagram maps a stellar population. Red giants cap out at a specific brightness before igniting, revealing a statistical inflection point. You see the cutoff at the top. Measuring this sharp edge derives distance without needing a variable star. When JWST captured I-band measurements of these red giants, the calculated expansion rate came in between 70.39 and 72.1. Replacing the middle rung of the distance ladder with an independent physical mechanism, the late universe expansion rate remains higher than the early universe prediction. To further eliminate the risk of photometric calibration errors, we have to look past light-based standard candles and rely on time. Massive objects curve spacetime into a lens. When a background quasar's light hits this gravity well, it splinters, taking multiple uneven paths to reach Earth. This schematic details a quasar lensing system. Because light paths differ in length, mirrored images of the same quasar flare arrive at slightly different times. Integrating that time delay through general relativity yields a geometric distance entirely independent of the distance ladder. Astronomers also use cosmic chronometers, deriving the expansion rate by measuring the change in time over redshift for massive, passively evolving galaxies. These kinematic methods return expansion values of roughly 73.3, corroborating the photometric ladder using different fundamental physics. Testing the late universe also requires measuring its total density. This reveals if late universe physics requires hidden variables in other areas. This brings us to the virial theorem, a tool to calculate a galaxy cluster's total mass based on the thermal velocity of trapped hot X-ray gas. Mapping gas temperature against cluster size locks in the gravitational mass required to hold it together. Calculations reveal a universal discrepancy, a staggering mass-to-luminosity ratio of roughly 300 to 1. To account for the gravity required to constrain that hot gas, the cluster mass must be dominated by non-baryonic dark matter. Attempts to explain away this missing mass with modified theories of gravity, like MOND, cannot account for gas profiles observed on these massive cluster scales. Just as local expansion measurements break early universe models, local density measurements demand physical mechanisms far beyond visible matter. This graph compiles the results of every independent late universe probe audited: SHOES, the tip of the red giant branch, strong lensing, and cosmic chronometers cluster tightly between 70 and 74. And isolated below them is the early universe prediction of 67.4. The hypothesis that the Hubble tension is a byproduct of local calibration, crowding, or dust has been systematically tested and largely eliminated. To bridge this gap, cosmologists must look toward unmapped phenomena, like early dark energy injections or structural modifications to gravity itself. The 5.8 sigma discrepancy has withstood every major audit of the local distance ladder. Its persistence suggests the lambda CDM framework lacks the physics necessary to describe the modern expansion of the universe.